GPTuner is a novel manual reading database tuning system, powered by large language model that leverages domain knowledge to enhance the knob tuning process. A knob is a configurable parameter which controls system behaviors. Tuning knobs appropriately based on the workload, data size, hardware, etc., can greatly improve the performance. Modern databases expose hundreds of knobs. It's expensive for humans to handle such huge amount of knobs in the cloud environment. In recent years, many machine learning-based automatic tuning systems have been developed. But they still encounter difficulties like high tuning costs and suboptimal performance, because they overly rely on black box optimization and oversee domain knowledge. GPTuner utilizes large language model to guide knob tuning. It mainly consists of three parts. Knowledge Handler uses a LLM-based pipeline to unify a structured view of the heterogeneous domain knowledge. Knowledge-based search space optimizer selects important knobs and utilizes structured knowledge to reduces the search space. And knowledge-based configuration recommender uses a novel course-defined Bayesian optimization framework to find out optimal configurations. To get started, we enter the first page, select DBMS. Here is Postgres version 14.9. We fill in the necessary information of the database, and offer the hardware information of the database. If the information is correct, we can now successfully connect to the database. We then select the model and provide OpenAI API key here. In the second page, we first select the target workload. TPCC and TPCH are supported by Benchbase. Here, we select customized workload for demonstration. We drop the workload files here. This time we upload Q1 to Q5 of TPCH. And then we offer a description of the workload. GPTuner has pre-selected important knobs for Postgres already. This time, we ask GPTuner help to select knobs for our customized workload. The selection process considers the features of the DBMS, workload, queries, and the dependency of knobs. The final selection results will be displayed here. We can check and modify the selection and finally click Save to submit. In the third page, we select shared buffers for illustration. The corresponding system view is displayed here. We have prepared knowledge from GPT, manual input, and web for most of important knobs. You can provide your tuning insight here. For example, we suggest to set it to 35% of the RAM. When you click the button here, GPTuner filters out knowledge which contradicts the system overview. In this case, the web suggestion is filtered because it offers a default value of 16 GB, while the default value provided in the system view should be 4 GB, which can be calculated by multiplying unit and reset val. Then with the selected knowledge, a summary can be generated. GPTuner can also help to check if the summary is consistent with the knowledge. Structured knowledge can be generated according to the summary, including minimum value, maximum value, suggested values, and special value. With this structured knowledge, the search spaces for our course-defined Bayesian optimization are optimized. In the course stage, the search space is discrete, represented by blue dots, while the search space for the fine stage is continuous, indicated by red lines, while the blue line indicates the default search space commonly used by most machine learning algorithms. Finally, let's start the tuning process. We initialize the optimization process with 10 samples obtained through Latin hypercube sampling, which results in a delay before the actual tuning process begins. The two-stage Bayesian optimization is visualized using two different colors, with the best performance being reported in real time. You can check the configurations of each iteration here and export the SQL file to deploy the configuration on your database instance.